Hello students, in our previous video, we saw how electricity can be generated using a phenomenon called electromagnetic induction. In today's video, let us learn about a device that produces electricity based on this principle, that is, an electric generator. Can you guess what an electric generator does? Unlike an electric motor, which converts electrical energy into mechanical energy, an electric generator converts mechanical energy into electrical energy. There are basically two types of generators, for alternating current and direct current. You already know that the terms AC and DC refer to the type of current flow in a circuit. In direct current, the electric charge flows only in one direction. The electric charge in alternating current, on the other hand, changes direction periodically. AC and DC generators both use electromagnetic induction to generate electricity. However, there is a difference in the construction of the two types of generators. Let's see how they work. An electric generator works on the principle of electromagnetic induction, where electric current is induced by rotating a coil in a magnetic field. That is, mechanical energy is used to rotate a conductor in a magnetic field to produce electricity. Now, let's see construction and working of an AC generator. A rotating rectangular coil ABCD is placed between the two poles of a permanent magnet. The two ends of the coil are connected to the rings R1 and R2. The inner sides of the rings are insulated. The two conducting stationary brushes B1 and B2 are positioned such that they press on the rings R1 and R2. The two rings R1 and R2 are internally attached to an axle. The axle can be mechanically rotated from outside to rotate the coil inside the magnetic field. Alternatively, an energy source such as flowing water or wind can be used to rotate the axle. The outer ends of the two brushes are connected to a galvanometer to show the flow of current in the given external circuit. When the axle attached to the two rings is rotated clockwise, arm AB moves up and arm CD moves down in the magnetic field. To find the direction of induced current, use Fleming's right-hand rule. The direction of the induced current is now from A to B to C to D. This means that the current in the external circuit flows from B2 to B1. After half a rotation, arm CD starts moving up and AB starts moving down. The induced current now flows in the direction from D to C to B to A. The current in the external circuit now flows from B1 to B2. Thus, after every half rotation, the direction of the current in the external circuit changes. Such a current that changes direction after equal intervals of time is called alternating current, abbreviated as AC. The device that helps generate such an alternating current is called an AC generator. Can you guess how a DC generator would be different from an AC generator? For this, let's see the construction and working of a DC generator. To get a direct current, that is DC, which does not change its direction with time, a split ring type commutator must be used. A commutator is a device that periodically reverses the direction of the current between a rotor and an external circuit. Here, the rectangular coil ABCD is made up of many turns of wire wound over a soft iron coil called the armature. The armature is placed between the poles of a strong magnet. The split ring commutator consists of two halves of a split ring, R1 and R2, made up of conducting material, separated by insulating material. The brushes B1 and B2 are in contact with R1 and R2 of the split ring commutator, respectively. R1 and R2 are connected to the arms CD and BA, respectively. When the coil rotates, arm AB will move downwards and CD will move upwards. The current will flow in the direction from D to C to B to A and onwards to R2. But externally, this current flows from B2 to B1 since R2 is in contact with B2. Now, the coil takes half a turn and brush B1 comes in contact with R2. And brush B2 comes in contact with R1 of the commutator. The current now flows along the path A to B to C to D and onwards to R1. But externally, the current will continue to flow from B2 to B1 because B2 is now in contact with R1. You will see that with this arrangement, one brush is at all times in contact with the arm moving up in the field, while the other is in contact with the arm moving down. Thus, a unidirectional current called direct current is produced. The generator is thus called a DC generator. How can we determine the direction of the induced electric current in the coil of a generator? This can be done using Fleming's right-hand rule. Stretch the thumb, forefinger and middle finger of the right hand so that they are perpendicular to each other. If the thumb shows the direction of motion of a conductor and the forefinger shows the direction of magnetic field, then the middle finger will show the direction of induced current. Hold your right hand between the poles of the magnet within the generator in such a way that the forefinger points in the direction of the magnetic field from the north pole to the south pole. The direction in which the middle finger points is the direction in which the induced current flows. The thumb shows the direction in which the conductor moves. So students, we have learned in this video how the principle of electromagnetic induction is used to generate AC and DC currents by respective generators. The direction of induced current can be determined by Fleming's right-hand rule. In the next video, we will explore domestic circuits.